some of my recent works, which I classify to computational mathematics or discrete mathematics. However, these considerations have many interrelations and applications in several areas of mathematics and computer science. In particular, they have some deeper algebraic background. So I plan to focus on presenting you this wider context of my study rather than giving all the details of particular results, which are sometimes very technical. I would like to emphasize that a large part of the problems I will discuss is inspired by works of an excellent mathematician, Professor Daniel Simpson, who unfortunately passed away about a month ago. Let me start with some basic notions. I fix a commutative ring of characteristic different than 2. For example, such ring, examples of such ring is the ring of integers or field of rational numbers, real numbers, or complex numbers. And in fact, these are the only rings I will work in this talk. So, by quadratic form, over the ring of ring R is a following mapping from Rn to R, given by the following homogeneous polynomial of second degree. And if the particular case when the R is a ring of integers, we say that Q is an integral quadratic form. Yes, so I already defined the first notion from the title of my talk, and the second notion, this incidence lattice, will be defined later. So it is convenient to consider such quadratic forms in the given by matrices, namely, I consider so-called Gram matrix of this quadratic form.
I would have a question.
Yes?
Have a question. Why this is just a quadratic form? Why this is called integral quadratic form?
Because it has integer coefficients, and sometimes we say integral coefficients. Yes, so this is this matter of terminology. It has nothing to do with integrals from mathematical analysis. This is just
or rather integer quadratic form, yes. Okay.
Yes, but some authors use also integral. Maybe it's a little confusing. Yes, I admit.
Okay, thank you.
Okay, so this upper triangular Gram matrix collects these coefficients. For example, here these coefficients lie here on the diagonal. So we call them diagonal coefficients, and the remaining coefficients lie above the diagonal. So, and when we have such matrix, we can present equivalently the quadratic form in such as a multiplication of the vector of variables from left and right by this Gram matrix. So this, when we multiply here these vectors and matrix, we obtain a scalar which is precisely of this shape. So this is kind of obvious observation. And we have yet another matrix, which is even more important. It's symmetrization of this upper triangular Gram matrix. Here by DR, I denote the matrix transpose. So this symmetric Gram matrix also encodes our quadratic form in this way. So, as I said, it's convenient to work with these matrices rather than such long formulas. So we say that two quadratic forms living on the same domain are equivalent over the ring R if they are the same up to some R automorphism of the domain. So we denote this by this symbol. So one can say that two quadratic forms are equivalent when they are equal up to invertible change of variables or up to base change. And again, it is convenient to translate this property into language of matrices.
So, excuse me, I have a question. Yeah, sorry. So, how is this composition defined? Q composition theta.
Here we have such thing: Rn, Rn. Here is Q, here is Q prime, and here is this theta. Yes.
Okay.
This is this diagram. This is natural composition of mappings.
Okay, thank you.
So this diagram commutes.
Okay, so we also know the similarity.
Yes, this is called also similarity.
Operation.
Yes, it's similarity, but it's over arbitrary ring, so so it is given by R isomorphism. And so it is much more convenient to express this property in the language of matrices, namely the symmetric gram matrices are congruent. Yes, congruence means that they satisfy this identity. But this matrix cannot be arbitrary, it has to be invertible. Equivalently, the determinant has to be an invertible scalar. Just quick reminder, if the ring R is a field, so each non-zero scalar is invertible. So this here we can just write for a field, we can just write that the determinant is non-zero. But for arbitrary ring, in particular over integers, the situation is a bit more delicate because we have only two integers which are invertible. Yes, so it is not enough to assume that the determinant is non-zero. You have to assume that the determinant is plus minus 1. And the general problem of which we can formulate here, which I am some far-reaching goal of my study, is to classify all quadratic forms with respect to this relation, or equivalently classify symmetric matrices up to congruence. So, of course, this is not very precise formulation of a problem because it may depend on the context. For example, we would like to have some simple invariance or maybe even algorithm who helps to test if two quadratic forms are equivalent, or maybe even we want something stronger, namely we would like to have a characterization of some canonical quadratic forms, some canonical representatives of each equivalence class. So it will be the best solution of such classification problem, especially when it is equipped with algorithm which determines the canonical form. And clearly, such general problem strongly depends on the ring working on. And for example, in at least 3 slightly different ways, we can obtain quite easily complete classification of real and complex quadratic forms. So this is just a reminder from linear algebra first year course. For example, each complex quadratic form is equivalent to such very simple and pleasant diagonal form. Yes, so here we have this R is small, can be smaller than n, so some variables can disappear. And again, similar arguments for real quadratic forms lead to the following also nice classification. But of course, over real numbers, we cannot take square roots of negative numbers, so we cannot get rid of these minuses here. So this is the only difference. So these facts provide a complete solution of the classification problem, especially that, for example, by Gram-Schmidt orthogonalization, we can have even algorithm for determining these canonical forms, and they are very simple. So we can read a lot of properties from these simple canonical forms. So what about the ring of rationals? Here the situation is in fact much more difficult because we cannot take square roots. One of the reasons is that we cannot take arbitrary square roots over rationals, and here there is no such simple classification. However, some classification is known, and it follows from beautiful part of algebraic number theory by so-called Hasse-Witt invariance defined over p-adic fields. So this is nice and deep theory behind it, and I'm not able to present it here. This is not my goal, but just to give you the flavor of the difficulty of the problems. And the most interesting for me is the case of integers. It appears that this is a very difficult open problem, and by some authors even consider that this is impracticable. So it means that this is impossible to give reasonable classification to whole class of integral quadratic forms. I will show some example, so maybe we will feel this more. Take such simple two variables quadratic form. We call such two variable a binary quadratic form. Here is the symmetric gram matrix, and it's easy to see that this matrix, we can directly check that this matrix gives induces the equivalence over real numbers, and of course over complex numbers too, with this diagonal canonical form. When we get rid of this irrational denominators, this matrix induces rational equivalence also with the diagonal form, but we have to have here the coefficient. Yes, here is the coefficient, and one can ask if this matrix gives also integer equivalence. Unfortunately not, because this is not invertible over integers, because the determinant is -2. It's inverse fractions. Even more, one can show that Q is not diagonalizable over integers. Yes, so for any matrix, it cannot be reduced to diagonal form. And I leave this as a nice exercise, as a homework, maybe. This example also helps to produce infinite by putting here some non-zero integer. I can produce infinitely many pairwise non-equivalent over integers quadratic forms. So we see that even for two variables, we have a lot of equivalence classes of integral quadratic forms. And there are, of course, some partial results on classification of integral quadratic forms up to Z equivalence. For example, binary forms where it is considered that they are completely discussed by Gauss in his famous dissertation. For a larger number of variables, a lot of famous mathematicians were involved in obtaining some partial results, which are highly non-trivial. So this is just, I don't want to talk more about this general result, because this is only to give you some context and some flavor of the difficulty which we are dealing with. And now I would like to give you a couple of concrete motivations or some deeper interrelation with another parts of mathematics or computer science. Namely, such integral quadratic forms, they induce nice Diophantine equations. I recall that Diophantine equation is the integer polynomial equation for which we search for integer solutions. These are the Diophantine equations. So integral quadratic forms induce specific Diophantine equations for some fixed parameter d. So this is nice, challenging equation, but what can we say more about this? The solutions of this equation, namely the vectors of integers which satisfy this equation, we will call d roots of a quadratic form Q. And I recall that Hilbert problem is a question whether is there a general algorithm which tests if a given Diophantine equation has a solution. And this Hilbert problem inspired a big part of 20th century mathematics, and after Matyjasewicz gave the negative answer for this problem. He closed the proof consisting of non-trivial results of many authors. And one of the crucial arguments he used was to show that the so-called Diophantine sets are surprisingly equal to recursively enumerable sets, which we know that are just Turing machines. Diophantine sets, roughly speaking, they are sets of coefficients of given Diophantine equation for which this equation has a solution. So roughly speaking, and it appears what is far from obvious that these three classes of of sets or computable models, computability models are equivalent. So as one can expect, that this search for the solution of this Hilbert problem was a nice stimulus for many branches of mathematics and computer science, computability theory, number theory, logic, but also integer nonlinear programming, some discrete optimization problems, graph theory, many other branches was stimulated by the search for the solution of this problem. Despite of a negative answer, it is still reasonable to search for some algorithms for certain subclasses of Diophantine equation. For example, this given by integral quadratic forms. Even more, we would like to also have algorithm which actually solve the Diophantine equation, which is a bit more difficult problem. And in this context, it is good to note that if two quadratic forms are equivalent, so this equivalence sends roots of one quadratic form to roots of another quadratic form. So we see that, for example, having a classification would help a lot in solving certain Diophantine equation. Yes, forms could be a helpful tool in this context. Of course, the classification is interesting itself, but it can have this application. So now we skip to number theory. So we can look at the same object from the point of view of number theory. Namely, several nice and known facts from classical number theory or algebraic number theory can be formulated, can be embedded in this context. For example, theorem of Fermat stating that every prime number is a sum of two squares of integers, if and only if this condition holds, can be expressed just in terms of integral quadratic forms. Namely, we can express this as that the set of roots of quadratic form, set of p roots of quadratic form Q is non-empty for quadratic form of this shape. Yes. So this is the Fermat theorem is in fact the question about integral quadratic form and its roots. Similarly, for famous theorem of Lagrange, it can be expressed obviously by non-emptiness of the set of roots of some integral quadratic form of four variables. Some similar result to Lagrange was given by Ramanujan for such quadratic form, a little bit more exotic, but this is exactly the same statement, yes, about non-emptiness of the set of roots. To also mention that Simpson generalized all these three results to large class of integral quadratic forms, not only such statements like Lagrange-like statements, but also algorithms determining concrete solutions, but for some specific parameters D. And this what is interesting, he observed that these three facts are in some sense such edge cases, the most difficult cases for which many other integral quadratic forms can be reduced. Of course, this reduction is non-trivial, it's very clever, but these three edge cases are the most difficult ones. So this is nice observation, maybe not well known, but I refer to Simpson's works. Okay, and third class of motivation come from algebra, namely integral quadratic forms, which are in fact small, simple objects. They appear in many contexts, many branches of algebra, algebraic geometry, topology, and they are often attached to some larger, more complicated objects in such a way that they reflect some certain properties of these objects, or sometimes the classification of this more complicated object can be reduced, at least partially, to classifications of related integral quadratic forms. because we are all the time I'm talking about I leave this in other rings. Examples which inspire my research come from algebra. Namely, if we have finite dimensional algebra lambda, I will explain in a moment the notions which I use here. One associates so-called Euler quadratic form, which is an integral quadratic form. Moreover, under some assumptions, it appears that some basic properties of this quadratic form, like definiteness. By definiteness, I mean that the question if the quadratic form is positive definite or positive semi-definite or indefinite, it is somehow related with the complexity level of the category of lambda modules. And even more, 0 roots and 1 roots provide classifications of indecomposable lambda modules. So this is also another application of this of this Euler quadratic form. Okay, so maybe I will very briefly recall the definition, because maybe not all of you maybe are very familiar. By algebra, I mean that this is a vector space. So we have some addition of vectors, and also here in algebra we have there is defined a multiplication of vectors, which is compatible with this addition of vectors in such a way that together they form a ring. So algebra is a structure which is at the same time vector space and the ring, and these two structures are compatible in the best possible sense. And this is associative and has a unit also. So for us, for this talk, it's enough such rough definition. And what about modules? Lambda module is again a vector space M equipped with an action of this algebra lambda. So we have some action. Sometimes it is considered from the left, sometimes considered from the right side, and this action has good properties, is bilinear, etc. So we have algebra, we have lambda module over the algebra, and mod lambda is a category of all modules, of all finite dimensional lambda modules. So I recall that category consists of objects. The objects are the lambda modules, and morphisms are homomorphisms of lambda modules, which are defined in natural way. So this is a big object we deal here, and it appears that it's controlled by a small object, which is a Euler quadratic form. Okay, so please forgive me that I don't give the details of this definition, but they are not necessary for this talk. Only some approximation is needed. Okay, so another example is Lie algebras, which are some non-associative algebras, which come from differential equations. And for such semi-simple Lie algebras, we have so-called Killing form, which is bilinear form over complex numbers. It induces also in some way integral quadratic form, and these integral quadratic forms were a helpful tool in classification of semi-simple Lie algebras. This is famous classification of semi-simple Lie algebras, which is, I hope, more or less known. I don't need the details of this classification. This is just an illustration. Yeah, so summarizing this, integral quadratic forms are simple objects attached to some more complicated objects, and they control somehow their properties in a non-trivial way. Okay, so now I will go to some. Now I leave these motivations behind and focus on the integral quadratic forms themselves. So I recall that I hope that I convinced you that the classification is difficult problem. So natural idea is to restrict the class of quadratic forms to some smaller classes. And for example, we can consider positive definite, shortly positive quadratic forms. It means that that they take positive values on all non-zero vectors. We can have a little bit more general notion, positive semi-definite, non-negative for short. It means that they have non-negative values on all the integers, on the integer vectors. And finally, we can have third restriction, so-called unit forms. And the only difference is that we have here ones. Yes. So these diagonal coefficients are ones. So this is some technical restriction, but it appears that these unit forms significantly simplify the classification problem. However, it is still non-trivial and in general open to classify all unit forms. But in comparison to a whole class of integral quadratic forms, it seems to be much easier. And even more, I would like to emphasize that from my point of view, these three restrictions are natural from the point of view of algebraic application, because the mentioned before Euler form is often a unit form. And I also mentioned that the definiteness is a relevant property in representation theory of algebras, for example. Yes, so working with these restrictions, we are still in the world which is interesting from the point of view of algebraic applications. So I would like to present now some concrete classifications of integral quadratic forms satisfying one of these restrictions. But to do this, I need some combinatorial notions. Maybe I consider sine graph, this kind of classical notion. So I treat it as a multigraph, and we have some sine function which assigns to each edge sine. And I consider a subclass of specific sine graphs, which are called edge bipartite graphs, shortly bigraphs. So this is a sine graph, which additionally satisfies that for each fixed pair of vertices, all edges incident with these vertices have the same sign. So this is such a technical property put to the sine graph. And now I would like to show you that each integral quadratic form can be encoded as a bigraph. And this is done in the following way. The vertices of this bigraph are just variables or indices of variables. And the edges are controlled by coefficients of this quadratic form. Namely, here, for example, here, these coefficients, if this coefficient is positive, so we take dij edges between I and j and put the plus sign. And similarly for negative coefficients, we take dij edges with negative sign. And what about these diagonal ones? So they will cause to appear loops in this bigraph, and these loops are defined in the similar way, but for some technical reasons I have to subtract one here. Yeah, so this bigraph can have loops. So let me see an example. Here is the quadratic form of 4 variables. So we have 4 vertices. Here I use the convention that the negative edges are drawn in as solid edges, and positive edges are drawn as such dotted edges. So this is common convention in drawing bigraphs. So for example, here we have -2. So it should be 2 negative edges between 1 and 4. Yes, so here we have 2 negative edges. Here we have +3, so it should be 3 positive edges between 2 and 4. And we have here this. Here we have 3 edges. And what about these loops? For example, here we have 2. So we have to have 2 minus 1. We have to 1 we have to have one dotted loop. And here is some hidden. Observe that here there is no x1 square here. So here we have 0 coefficients. So 0 minus 1. So we should have one continuous edge in vertex 1. Yes, so this small technical nuance with these loops. And in this, so it is easy to observe that in fact this construction is bijective in the sense that there is integral quadratic forms and bigraphs with fixed set of vertices, and this bijection restricts to the bijection which sends unit forms to loop-free bigraphs. Yes, because observe that if here we have +1 coefficient, it makes the vertex 3 has no loop. So this is such nice encoding of integral quadratic forms. So now I have everything to present one of the very first results of unit forms. It's due to Ovsienko, Ukrainian mathematician, and he considered the smallest possible class because he joined the positive and unit integral quadratic forms. So this is relatively small class of integral quadratic forms. They are also graph is connected. This is not very important assumption. So it states that each quadratic form is z equivalent with a quadratic form whose bigraph has one of the following shapes. And observe that these shapes have only negative edges, so these have on negative coefficients or diagonal coefficients. And here we have two infinite classes. Here is greater equal than 4, and 3 exceptional cases. And they are called in the literature Dynkin graphs. And I should mention that these Dynkin graphs, they appear in many mathematical contexts. For example, in Lie theory, they in fact originate from Lie. And this is a mystery. I mean, this is still not well understood. What is the reason that these shapes appear all around mathematics? Yes, so it seems that it is some immanent property of mathematics or of reality. And they appear also in this context of integral quadratic forms. So the classification is quite simple. And I would like to again say a word about algebraic context. And again, please forgive me to not define every notion appearing in this theorem. But here we have the finite dimension algebra over a field which is algebraically closed, like for example complex numbers. And here we have kind of strong assumption. This is kind of homological assumption. It states that so-called global dimension of algebra or homological dimension is not very big because it is at most 1. So this is small class of algebras, but important for many reasons. And this theorem states that such algebra has finite representation type. And this means that there is only finite lambda modulus up to isomorphism. And this property holds precisely when the Euler form, which is unit form in this case, is positive. So in particular, applying Ovsienko theorem, we have classification of hereditary algebras of finite representation time in terms of Dynkin graphs. So again, Dynkin graphs appear in another branch of mathematics. And moreover, it appears that in the composable objects up to isomorphism, in the composable modules up to isomorphism are classified by 1 roots, which are additionally positive, which have positive coefficients. So this is powerful theorem for a relatively small class of algebras, but it really illustrates the idea which I was trying to advertise you at the beginning, that these Euler forms control non-trivial properties of some larger objects. So this is for hereditary algebras and positive quadratic forms. And later, many authors generalized this theorem to much larger classes of algebras, and they involve, these classifications involve also non-negative unit forms, or so-called weakly non-negative unit forms. And some of these results were really breakthroughs in this branch of representation theory of algebras. Of course, I have no chance to speak about these results. This is only an illustration and the motivation to study non-negative unit forms. Negative unit forms, I have to say that they have this nice property that the kernel of a non-negative integral quadratic form, not necessarily unit, that is the set of zero roots, is a subgroup of the domain, which is in general not true, because quadratic form is not a linear map, so kernel doesn't have to be a subgroup. But for non-negative forms, it is a subgroup. So we can say about its rank, and we call this rank of the kernel the corank of quadratic form. And having this notion of corank, I can present the generalization of Simco theorem from positive to non-negative unit forms of corank C. And it appears that they are also classified by Dynkin graphs, which we call the Dynkin type of a quadratic form. But also this corank is involved in this classification. Namely, observe that here some few variables disappear in this canonical form. So in the language of bigraphs, this canonical form is of the following shape. You have Dynkin graph, and these missing variables, they, as I showed you before on example, they induce the isolated single solid loops. So this is canonical form of a non-negative unit form. So this is very nice classification and strong generalization of Simco result. But for some reason, these canonical forms are not very nice because they are disconnected and they have loops. And for this reason, Simpson and Zions, they gave alternative classification by connected and loop-free shapes, which I won't mention it here because it is kind of complicated, but for many reasons it is better for applications. This classification of Simpson-Zions, alternative classification of this Baroque de la Peña. So now I would like to speak about some alternative approach to negative unit forms, alternative to this Baroque de la Peña, Simpson-Zions, which has some potential to, for example, to compute Diophantine solutions of Diophantine equations. So we consider this Jesus Jimenez is from Universidad Nacional Autónoma de México. He will be our guest, the guest of our center. He arrives, I hope, in August for 4 months. We are collaborating since some time. And we consider such, at first sight, weird combinatorial objects like bidirected graphs. They are graphs for which we associate to each edge, we associate such multiset of signed endpoints. So each edge has assigned 2 signs. And this can be interpreted in the following way, that if you have edge which has sign +1 and -1, we interpret the plus signs as a starting point of an arrow and minus sign as an ending point of an arrow. And when you have 2 pluses, so we have such arrows which have 2 starting points. And when we have 2 minuses, we have arrows with 2 ending points. So such bidirected graph is a directed graph which admits such ambiguous arrows which have 2 ending or 2 starting points. And it appears that they nicely describe some class of non-negative unit forms. So now I would like to show you how we associate an integral quadratic form to such bidirected graph. Namely, so I will, instead of defining integral quadratic form, I will define its bigraph, because as I said before, quadratic forms and bigraphs are in bijection. So once we have a bidirected graph, we construct the bigraph. The set of vertices of this bigraph is a set of edges of the bidirected graph, and edges of this bigraph are induced by edges of bidirected graph which are incident in this bidirected graph, which means that they share common vertex. So it remains only to, I will show an example in a moment. So it remains only to define signs of this bigraph, and we put -1 if these two edges are composable. Composable means, roughly speaking, that the ending point of one arrow meets starting point of another arrow. So this is kind of intuitive notion, and +1 otherwise. So for example, here we have bidirected graph and corresponding bigraph. So we have here four edges. So this die has 4 vertices. And for example, let me check if 2 and 3 are composable. If we go here, so here is ending point and here is starting point. So yes, they are composable. So we have a negative edge between 2 and 3. For example, here we can, here ending point meets starting point. So we have negative edge here. But here we have another negative edge because I can go also in this way. And so on. So we see that the shape of these two objects can be completely different, but this is some kind of nice procedure to build one from another. And this bigraph on the right hand side, it induces integral quadratic form, which we call an incidence quadratic form. And it is quite easy to observe that such incidence quadratic form, its diagonal coefficients are cannot be very large. Namely, they are, and even more, they are all ones. So form is a unit form precisely when this bidirected graph has no loops. So this is kind of technical and simple observation, but much less trivial observation is the following: that such quadratic form, incidence quadratic form, is always non-negative, and even more, it had Dynkin type A or D. So we exclude these 3 exceptional cases, E6, E7, and E8. And conversely, each non-negative unit form of this Dynkin type can be obtained in this way. So both these implications are non-trivial, and they require a lot of ideas. And why we do this? It appears that from this bidirected graph we can read many properties of the quadratic. Only 2 here. For example, we can read that the Dynkin type is D precisely when there is closed walk with odd number of two-headed arrows. So let me check how it looks in this example. Here, this is the only closed walk is here, and here we have two-headed arrows. So here is even number of two-headed arrows. So this is Dynkin type A. It means that this is Dynkin type A because this condition is not satisfied. So we have gratis, without any computations, the Dynkin type. Even more, we have formula for the Korang. This is the Kronecker delta. So let me compute in this case. Here we have 4 vertices, 4 edges. We have also 4 vertices, and the Dynkin type is A. So the Kronecker delta is 1. It means that the Korang is 1. Yes, so it gives us, without doing almost no computation with any matrices, we have Dynkin type and Korang from this construction. And another application, which is in fact even more important for some reason, is that we can describe solution of Diophantine equations by graphs. Not all solutions, but there is some specific. So namely, once we have this bidirected graph, we can we constructively define some mapping. So I don't give the description of this mapping, is technical, but then it's constructive, and it is constructive, which sends each walk to in this bidirected graph to some integer vector, and it appears that all vectors which appear in this way up to sign, so the plus minus image of this map, it encodes all 0 roots, all 1 roots, and some of the 2 roots. And even more, this left inclusion is an identity precisely when the Dynkin type is A. So observe that this immediately provides new and efficient polynomial time algorithmic methods to determine solution of Diophantine equation of a very large class of integral quadratic forms, but only for specific D, yeah, because only the 0, 1, and 2, mainly 0, 1. But as I mentioned before, that these 0 roots and 1 roots are especially important from the point of view of algebraic interpretation. So this is, of course, this requires some work. I mean, we plan to do some generalization of this theorem, and we will work when he arrives here, I hope. But all of this was mainly for unit forms, yes, for this kind of small artificial class of integral quadratic forms. So what about non-unit forms? Yes, so we want to go beyond this simple class. I recall that upper triangular Gram matrix looks as follows, and here Kassen and Simpson in 2015 proposed the following definition. The integral quadratic form is called Cox regular if it's Coxeter, so-called Coxeter matrix, which is given by this coefficients. So let me stop for a moment to understand this definition. It's well defined. It means that the Gram matrix is invertible. So look, this is upper triangular matrix, so it means that here we cannot have zeros, yes, so that the i's are non-zero. So this is well defined, but the fact it belongs to integer matrices is a little bit more subtle, because observe that upper triangular matrix, it is upper triangular, so this is always, if it is invertible, so it's invertible over a lot of fractions, and here we assume that if we multiply by the transpose, all the fractions disappear. So this is clearly not always the case, but this class is still very nice, because, for example, each unit form is Cox regular, yes, because unit forms have ones here, so such matrix is clearly invertible over integers. But from unit forms, we can produce infinitely many Cox regular forms by simply multiplying it by some non-zero integer. But this is kind of not very interesting. We are mainly interested in such Cox regular quadratic forms which are not multiples of unit forms, and it appears that there are many of them. Here is one of the examples. So this is for sure not a multiple of the unit form, and observe that the upper triangular Gram matrix is like this. So it's easy to see that the inverse have some fractions, but when we multiply it by transpose, it appears that all the fractions disappear. So it is indeed Cox regular matrix. So this is, of course, this definition seems a bit artificial, but it appears that this Cox regular matrix have again some interpretation in algebra. Maybe I will mention at the end something about this, but I see that I'm already close to the end. So what about this Cox-regular quadratic forms? Here for some technical reasons coming from algebraic interpretation, we consider stronger relations that not only they are Z equivalent, but also number of loops coincide. Yes, because they are not units, so their bigraphs have loops. And in general, the Z equivalence does not preserve loops, but we assume that the loops coincide. So we have stronger relations. So in fact, the classification problem is slightly more difficult. And we obtain, as a collection of theorems, in fact, the following generalization of Ovsienko theorem for Cox-regular quadratic forms. We assume that they are irreducible, so it means that they are not multiples of another Cox-regular. So these irreducible are the most interesting ones. All other can be obtained as multiples of these irreducible ones. So first of all non-negative Cox-regular quadratic forms with small corangs, namely corang 0 or 1, are classified analogously as in Ovsienko theorem by the following shapes. And observe that corang 0 is precisely positive ones. And Cox-regular contain unit forms, so the Dynkin graphs have to appear here, yes, and they appear here. This is Ovsienko theorem. But here we are beyond unit forms, so we have also another shape. So this is corang 0. That is this positive quadratic form. Yes, non-negative of corang 0 is positive, and the remaining are corang 1. For higher corangs, this is still open problem, but we have some ideas how to solve it. But what is more important, that this classification is constructed in the sense that concrete algorithms which determine this canonical forms, and this algorithm have arithmetic complexity quadratic, respectively cubic in corang 0 and 1. So is it high or is it low complexity? Let me compare with some other. But before they were algorithms for positive and unit quadratic forms, yes, because this Cox-regular are quite new notion. So for unit forms, there are several algorithms to determine the Dynkin type, and they have various complexities. So I emphasize one more time that positive, so this is this case, and here is unit forms, and we are Cox-regular, so we are in more general setting. So this is this complexity, yes, so we significantly improves the complexity. But I should also mention that there is also a Mexican group, which in some sense independently work on similar problems, and they developed a cubic algorithm for positive quadratic forms. But anyway, this is still worse than ours, quadratic. And for corang 1, our algorithm is kind of new. There is no other algorithm we can compare. So one of the applications of our result is that we can use this algorithm as an efficient positive definiteness test for arbitrary Cox-regular quadratic form. I recall that positive definiteness test can be obtained by applying Sylvester criterion supported by Gaussian elimination, and our very non-standard algorithm has better complexity than this standard algorithms. So arithmetic complexity is quadratic, and I hope it's clear that Gaussian elimination is cubic, so it's better. But if we go a little bit deeper and we compute bit complexity, so since our algorithms operate on small integers, they have the bit complexity is almost the same as arithmetic complexity. In Gaussian elimination, has exponential bit complexity because numerators and denominators can grow exponentially if we do it in some naive way. Of course, there are some better implementation of Gaussian elimination, but here I compare with the standard one. So our algorithm has chance to be in practice much better than this standard test. And in fact, I did some benchmarks. I compared our algorithm to test positive definiteness of integral quadratic form. I compared it with standard Maple routine is definite, and also just in case with our efficient implementation of Gaussian elimination. So we see the difference. Yes, this red is here, and so here is the number of variables. Yes, and here are seconds. So these two guys grow quite quickly, and our algorithm is very fast, and the reason is that the low bit complexity, in fact. Okay, so we also give some characterization of all non-negative Cox-Ribot quadratic forms. I mean, in the sense that we gave strict bounds for the coefficients. Maybe it's not very important all the details of this result, but only observe that diagonal coefficients have to be between 1 and 4, and non-diagonal coefficient can be at most 8 up to sign. So this is kind of nice characterization, but it's kind of first step in order to classify all the non-negative Cox-Ribot quadratic forms. So I obtained these results with my former student Bartosz Makuracki, who defended his PhD thesis recently. This PhD thesis contained these results, which I'm speaking about. And we obtained also a lot of other results concerned with this non-negative Cox-Ribot quadratic forms. But I, of course, have no chance to speak about them, and it doesn't make sense because they are quite technical. I only mentioned that we have some results inspired by Lie algebras, and here some results also by associative algebras. So we have some very specific technical results which have some applications in this Lie theory and representation theory of associative algebras. And okay, I see that my time is almost over, but I still didn't define this second object of my title. So if I could get 5 or 7 minutes more, I could very briefly finish the talk. Is it okay?
Yes, it's okay. I hope that the audience will survive. So let's try.
Okay. I also hope. So I promise that I omit the technical details. I only focus on the ideas. So there is such thing like bilinear lattice. This is a triple consisting of abelian group, bilinear form, and automorphism, and they satisfy some formula. So this is kind of discrete object, a triple. Yes. So I skip some properties, and again, to algebraic background, if we have algebra, finite dimensional algebra, we can complicated way the bilinear lattice associated to this algebra. So I omit completely the details; they are not important. I just want to give you the taste of the character of these results, and observe that we have the Euler form, which I was mentioning at the beginning, is the part of this formalism. So we have algebra, and we associate this discrete object, this bilinear lattice, this triple group, bilinear map, and automorphism to algebra. And this bilinear lattice is called Euler lattice. Here I list some properties of this Euler lattice, which I also have no chance to discuss. And in fact, this is not very important because it's still an illustration. But only what I would like to pay attention that we consider so-called derived equivalence of algebras. we say that two algebras are derived equivalent if their so-called derived categories, their huge categories containing module categories, are equivalent. And this implies that these Euler lattices are isomorphic. And in particular, the quadratic forms are equivalent. So this is the motivation, another motivation to study equivalences, because they control derived equivalence of algebras. And it's also, I think, interesting to mention that these derived categories, which I have no chance to define here, and derived equivalences, they can be considered for arbitrary abelian category. For example, they appear in algebraic geometry and other branches of representation theory of algebras, but also in mathematical physics. This is a nice tool in string theory, this derived equivalence. And I only mention as an illustration that I have some results with José Antonio de la Peña in this direction, that we are reading some information on derived category from so-called Coxeter polynomial, which is another invariant of this bilinear lattice. Okay, so summarizing, we have algebra, and we associate to it some discrete objects Euler lattice, which controls, among others, derived equivalences of algebras, which is important relation in the world of algebras. And this what I am doing with Jesus Jimenez is we want to equip this bilinear lattice with our weird object, this bidirected graph. Yes, so this incidence lattice, this second object from the title of my talk, is the bilinear lattice equipped with compatible bidirected graph. And we have several properties which I also omit. I only mentioned that we have some invariant of isomorphism of this incidence lattices. This invariant we can read a lot of information on other invariants from this bidirected graph. Again, I have to skip it. Here I compute some example, but maybe again I will skip it. So sorry that I don't go into details, but I'm going straight to the main result of this concerning this bilinear lattice. We consider class of algebras called gentle algebras, which again I have no chance to define here, the kind of technical definition, which is not as important as applications of this class of algebras, which, please forgive me, I also skip it. I will go straight to the main result. So we proved that for such gentle algebra, we can, in a constructive way, we can associate the bilinear incidence lattice. So in particular, we have gratis a lot of nice properties of Euler forms for this class of algebras. And even more, we have very nice new derived equivalence invariant for gentle algebras. See, here is some example. Okay, so I can stop in this moment. This is the final slide. So again, excuse me for going so briefly in this final part. But I think the most interesting was this motivation part at the beginning. So thank you very much for the attention.
Thank you. So it was thank you for a very interesting talk. Let's say, you know, about diagonalization. Yes, diagonalization, different rings. I would have first question. First question is, if we consider, let's say, finite fields like residual fields or final rings, yes, so we have zero divisors. Do we have some classification of quadratic forms?
I don't know much about this context, but I only mentioned that as far as I know, the problem is with this. If we have, for example, field of characteristic 2, we have field
of course, yes.
F2. So there is no nice interrelation with matrices. We don't have this. This is not.
Yes, but it is only restriction characteristics. But for bigger, for rings of higher characteristics, when there is not a problem, do we know something or not?
If this ring is a field, so each quadratic form over a field can be diagonalized. But this is the only thing we know, because these diagonal forms can be also complicated because they have complicated coefficients, like this situation over rationals. Yes, so over fields we can always diagonalize by using some generalization of this Grashnik orthogonalization. But I don't know more about to do next after diagonalization.
Okay, but at least we know something for fields. So thank you for your answer, and we wait for next questions. Do anyone has a question? Does anyone have a question? Okay, so
I think there is a question by Professor Duch. I can see the hand.
Yes, I have the hands up and I'm trying to get attention over.
Okay, sorry, I don't see that. I don't see the hands, so I cannot react.
yes.
I thought that everybody should see the hands up. Well, I just wanted to comment that in 1986, I've published a book on graphical representation of model spaces. And since the graphs were representing integers 0, 1, 2, which are the occupancy of orbitals in quantum mechanics, I wanted to represent the tensorial space or the Hilbert space with proper symmetries that can be used to project, let's say, differential equations, the Schrödinger equation into the discrete space and change that into algebraical forms. And the graphs that I had to implement there were of this sort, that they had 0, 1, or 2 occupancies. Therefore, actually, I've started to look at this Diophantine equations, linking diagrams, and lots of other things. And I've added in the, and so you may find it an interesting also application of this type of mathematical problems. I've added in the chat the link to the preface of my book, where I write about motivation to do this sort of things. And of course, I haven't followed that since that time that much, since I've changed my field of interest, but you may perhaps find it interesting from the point of view of possible applications of the work you're doing. So that's my comment.
Okay, thank you very much. Thank you very much. I see that. I see this.
Yes, the title is. I think the title is about that. And when you look at the table of contents, you will find also the algebras and other skills in the book that was quite useful to the graphical representation of model spaces. It was quite useful for building practical applications for the solutions of Schrödinger equations in these finite dimension spaces. So, And
Okay,
there's lots of
thank you.
problems that I have not solved related to complex symmetries that we can use in physics, especially in atomic physics. I've left it for the volume 2, which was never written. So
Okay.
I hope that maybe somebody will find some interest in this. Okay.
Yes, it seems very interesting. Thank you very much.
Okay. Do anyone else? Does anyone else have a question?
Yeah, I have a question. So you proved, I mean, with Jimenez, that this incidence B graphs or directed graphs are of importance, yeah, because they characterize those non-negative forms of Dynkin types A and D. Do you have an internal characterization of this incidence B graphs?
But what do you mean by internal?
Yeah, I mean, so that you have a B graph, and by looking at some properties of it, you can determine whether it is an incidence B graph of something or not. Or is there a kind of construction how to construct this bidirected graph?
Yes. It is constructed, but it's complicated.
But this construction somehow also finds, I mean, you can start this construction, say, on any B graph.
Yes. Yes.
Does this construction somehow tells you, so it fails in some moment and it tells you, okay, it is not an incidence B graph, or can you see it from the beginning that it is not an incidence B graph? How it works? Or will it indefinitely, so it has no stop property?
There is some
wrong B graph.
Okay, I understand. So there is some procedure, and it will fail at some moment, and we can detect this failure. I mean, we can kind of characterize the moment the procedure fails. Yes, but this is not this is more algorithmic than theoretical criterion.
Okay, I see. Thanks.
May I?
Yes.
So in your very last theorem, it is stated that for gentle algebras, derived equivalence implies equivalence of these associated lattices. Can you comment on the inverse implication?
No, we are working on this. This is our far-reaching goal to this. I mean, set of integers here. It is somehow equivalent with this AAG invariance, which Grzegorz Bobiński was talking about, this Alvino-Geis invariant. But there is a chance that we can inverse the implication for precisely the same classes of gentle algebras as Alvino-Geis. But there is our invariant much simpler conceptually.
Okay, thanks a lot.
But this is work in progress. Yes, so I have no final answers to this.
Thank you.
Okay, are there any other questions? So thank you for your questions. I would like to thank the speaker for this interesting talk, and this is the end of our seminar. Next seminar, I think, will be Kamil Bona from from a deputy of applied informatics. So you will obtain an announcement about it. Okay. So thank you. Bye.
Thank you very much.
Dziękuję bardzo.
Thank you and goodbye.
Thank you. Bye.
Thank you. Bye.
I would like to ask, because I saw that it was recorded, is this recording available somehow?
Yes, so recordings, yes, they will be available on our YouTube channel, and we will send the link. I think I send these links, but quite regularly. But last talk and this talk yet wait for be announced to be available.
Okay, so I hope that you inform us. Okay.
Yes, I will.
Thanks. Okay, thank you. See you.
Okay. See you. Bye.
Bye.
Okay, so I end the meeting for all.